So in our previous class, we have discussed about basic of the rheological model. We have discussed about relaxation response and tip response. So in that case, we have given some example that how the viscoelastic nature of the bituminous material can be formulated or mathematically can be represented. So basically what we have discussed that we can represent the elastic properties of the bituminous material with the help of spring and the viscous property of the bituminous material with the help of a dashpot. Now for the spring, a spring model, so if you go for a simple spring model, a spring model is made up of simple spring where stress is proportional to strain and one constant is there that is called spring constant, and basically the definition of the spring constant is the unit deformation. For the unit deformation, how much stress should be applied over there, that is your spring constant. Okay, now for this spring constant remain unchanged with respect to the level of stress and the strain rate. So basically that spring constant, why it is called constant, because for each and individual spring constant is a constant term which remain unchanged based on the stress and rate of strain. Now for the creep behavior, okay, for the creep behavior means when stress is constant, as our previous case. For the creep behavior, our strain would be sigma 0, that is that stress divided by Ks. Ks is the spring constant. Okay, so for the creep behavior, when stress is constant, in that case our strain would be stress divided by spring constant. And for the relaxation behavior, when the relaxation behavior happens when strain is constant, in that case your stress would be spring constant into constant strain. So basically if you go for the definition of the spring constant, the definition of the spring constant is nothing but your Ks equal to, here it would be stress divided by your strain. Okay, now the thing is for the creep behavior, which factor would be constant, that is your stress would be constant, so therefore stress is 0. So for the creep behavior, when your stress is 0, you have to find out what is the strain. So your strain would be basically for the creep condition, that would be your spring constant into your sigma 0. Basically here sigma 0 represent the constant stress. Okay, therefore it is sigma 0. And similarly for the relaxation behavior, so in the relaxation behavior your strain value is constant, so you know what would be the rate of the strain, but in that case your stress is not constant, so you have to find out what is the stress. So in such cases, here epsilon 0 basically represent the constant rate of strain, so you have to find out the stress. So your stress would be spring constant into epsilon 0. So therefore the constitutive relationship of a Hookean spring means the spring which obey the Hooke's law. That is, what is Hooke's law? Hooke's law is within the elastic parameter, stress is proportional to strain. So that can be represented as sigma equal to Ks into E, so which we have already discussed, where sigma is the stress and stress in the spring, Ks is the spring constant, and E is the epsilon is the strain in the spring. So basically we have already discussed what is spring constant. So your Ks would be stress divided by strain. So for the Hookean spring, that is the spring which normally follows the Hooke's model, that is a Hookean spring. So in that case, for the creep condition, when your stress is constant, in that case, see that is that is for the strain. Your strain would also be constant. Why strain is also be constant? Because that is a Hookean spring, and in that case stress is proportional to strain. So if stress is constant, in that case strain will also be constant. Okay, and for the relaxation case, what is the constant value? So relaxation case, the constant value is strain. But for the Hookean spring, what happens? As the stress for the Hookean spring is proportional to strain, and as the strain is constant, therefore your stress would also be constant. Now this is all about the spring. Now let us discuss about the dashpot. So a dashpot causes damping in a structure. In a dashpot, the stress is proportional to the strain rate. So here's the difference between spring and dashpot. Dashpot is, in the spring your stress is proportional to strain, but in case of the dashpot your stress is proportional to the rate of strain. Okay, that whether the rate is increasing or decreasing, or whether there is a constant rate. So basically the rate of strain is here constant. So in such cases, your creep behavior is when stress is constant. So here sigma equal to, that is your viscosity into strain rate. Okay, this parameter is strain rate, where sigma is the stress in the dashpot, that is nd is the viscosity of the dashpot, and epsilon dot is the strain rate of the dashpot. Okay, so that is for the creep behavior, or for the dashpot. That is actually main thing, your sigma equal to nd divided by rate of the strain. So in that case your viscosity would be basically defined as that rate, the stress divided by the rate of strain, stress divided by the rate of strain for that dashpot material. Now as you can define that your viscosity equal to stress divided by rate of strain. So if you derive this, okay, so dE divided by dt. So basically that is the rate of strain. So basically that is nothing but the your derivative form. Okay, so if you move it over there and put it over there, you can write down that now this form is nothing but, so why it is so? Because that is nothing but the rate of strain, and rate of strain, basically strain changes with the time. So basically it varies with the time. Therefore, it is in this equation, that is equal to sigma divided by ND. Okay. Now ultimately, if you go for the integration from 0 to your sigma, that is 0 to your full strain, then dE equal to 0 to T sigma divided by nd, and if you derive this you can get here strain equal to, it would be sigma. So for the, for your constant condition, your sigma is constant, so basically that would be sigma 0 into T divided by nd. Okay, so this, that is for your creep condition, that is for the creep condition where when your sigma is, or when your stress is constant. Now for the relaxation behavior, what happens? For the relaxation behavior, your rate of strain would be 0. So this particular term, rate of strain, is 0. So if you go for this equation, if rate of strain is 0, in that case, that particular term, that is your sigma, will also be 0. Okay. If you go for this equation, in this case your sigma will also be 0. So for the relaxation behavior, what does this indicate about the dashpot? So for the dashpot, whenever your stress is increasing, your rate of strain is also increasing, and but when your rate of strain is stopped, in that case your stresses in the body is also 0, also negligible. So basically it really indicates the viscoelastic properties of the bituminous material. In the bituminous material also, whenever you will apply some load, in that case there would be some deformation, and whenever you just reduce the load or remove the loading condition, in that case bituminous material in somewhat will gain to its original position. So that means if there is no load in that case, or if there is no stress, in that case there would be no rate of strain, or if there is no rate of strain, in that case there would be no stresses in the body. So basically that represents by the relaxation behavior of the dashboard. So if you model this, if you can model about this, that is the Newtonian dashboard. Newtonian dashboard means, as the dashboard represent the viscosity, so the Newtonian dashboard is the dashboard which follows the Newton's laws of viscosity. Now for the creep condition, so that would be graph for the creep condition. Basically here your that is your strain would be constantly changes with your time, but for the relaxation condition, as your rate of strain would be 0, rate of strain would be 0. Basically in the relaxation case your strain is constant, so your rate of change of strain would be 0. In that case your sigma would also be 0. Now various combination of spring and dashpot are used to develop various model. Now since these models are made with elastic is that is spring, and viscous, that is dashpot, so therefore this combination of this spring and dashpot represent the viscoelastic nature of the bituminous particle. So I think it is clear to you how the spring and dashpot are functioning. So let me discuss this again. For the spring, here one spring constant is associated. Spring constant is basically the unit pressure needed for the unit displacement. Pressure needed for the unit displacement. So you can define spring constant Ks equal to as your sigma or stress divided by strain. Okay, strain basically represent the deformation of the body. Now the for the relaxation behavior there would be two conditions. One is creep and another one is creep and another one is relaxation. So for the creep behavior your stress is constant, and for the relaxation behavior your strain would be constant. So in the creep behavior, whenever you are your stress is constant, in that case you have to find out what is the strain. So from the definition of the spring constant you can easily find out what is the strain. So your strain would be your constant stress divided by your spring constant. Now this spring constant will be similar for the same spring. Okay, it will not change according to the loading condition, therefore it is called spring constant. So in this way you can represent the creep behavior, or you can find out in the creep behavior what is the strain. Now similarly for the relaxation behavior, when your strain would be constant, in that case you have to find out what is the stress. Then stress would be your spring constant into constant strain. So therefore the constitutive relationship of a Hookean spring means the spring which follow the Hooke's law, where stress is proportional to the strain. It can be represented as for the Hookean spring. So for the creep behavior, what will happen? For the creep behavior, your stress is constant. So if stress is constant, in that case, for the Hooke's law to be followed, in that case, strain must be constant. Therefore, strain rate is also constant in that case. Okay. And for the relaxation behavior, what will happen? For the relaxation behavior, your strain would be constant, and as the spring follows the Hooke's law, in that case your stress would be proportional to strain, so your stress is also constant. So that is spring. Now for the dashpot causes damping in the structure, and basically it represents the viscosity properties of the material. So for the dashpot, the main thing or main viscosity of the dashpot is defined as your viscosity equal to stress divided by the rate of strain. So that is the difference here. In the dashpot, your uh, rate of strain would be proportional to stress, or stress would be proportional to rate of strain. So here in that case it is rate of strain, but for the spring case it was only strain. So in the spring case, the difference between these two is, in the spring case your stress is proportional to strain, but for the dashpot your rate of strain is proportional to stress. Now, if that is your equation, your sigma equal to nd into rate of strain, in that case, you can write this equation like that, your nd equal to sigma divided by epsilon dot. So if you can transfer this over here and move nd in the below, in that case, you can expand this term. Okay, expand this term. So if you expand this term, particular term, it would be d by dt into sigma divided by nd. And if you integrate this, you will find epsilon equal to sigma 0, as that is would be constant, divided by your nd value. So basically that is your strain in case of your creep condition, in case of creep behavior. But for the relaxation behavior, what happens? In the relaxation behavior, as your strain is constant, so your what would be rate of strain? Rate of strain would be 0. So if your rate of strain would be 0, in that case, from this equation you can find out that your sigma would also be 0. So that is 0. Okay, so basically that represents this relationship in the creep and relaxation case. So various models have been designed or have been postulated based on the spring and dashpot. So some of the models are very basic model. These are two components model. So basically in the two components model, a series of combination of spring and dashpot is known as Maxwell model. So in there are different models like Maxwell model and Kelvin model, like that. So in the Maxwell model, what happens? A series of spring and dashpot would be connected in a series connection. There will be two types of connection: series connection and parallel connection. So in a series connection, they would be connected. So this type of model is called Maxwell model. Now in another model, what happens? That all the spring and dashpot will be connected by parallel connection, and in that type of models are called your Kelvin-Vogt model. So we'll discuss this Maxwell model and Kelvin model in our next class. Okay. Okay, you can leave the class.